My name is Vikram. I'm from the Qualcomm Linux scheduler team, presenting some data on WALT versus PELT for CPU utilization tracking on x86 specifically. This is part of an effort to get WALT upstream, or to start a conversation at least on LKML. And this is like a first preview or a first step towards that. Sorry for I heard my voice earlier on the mic. It's pretty horrible, so sorry about that. This is the agenda. I've assumed that's folks that have attended previous Connects. Steve Muckle presented some of my slides at Bangkok, so I'm assuming some level of familiarity with WALT and PELT, but I do have an introduction. I'll describe what we've done for the RFC patch that we posted to EAS Dev. Srivatsa Vadagiri, who's the original, he had the original idea for WALT. He basically helped clean up and reduce the patch set to just CPU utilization tracking, and we've removed the task utilization tracking for now. And then I'll present results on x86. I've used the Phoronix test suite results, which I think is a nice segue into that because of Steve Muckle's experience with trying to get a test suite going for ARM. So PELT was introduced by Google, Paul Turner in 2012 to address some of the load balancing and load tracking concerns that were present at that time. It uses a geometric series to decay load and utilization. Some of the rework that's come into the kernel recently from Yu Yang Du from Intel makes it such that both block load and active load is tracked in the same util average statistic. So it was separated, but it's no longer that. The PELT math right now decays load such that whatever load was seen 32 milliseconds ago contributes 50% towards the current average. Those are the two PELT utilization statistics. Load average contribution of I should say utilization there, utilization average contribution of a single sched entity and averaged over the run queue. This is a bit of a, I'm sorry about these slides, they're a bit texty. I didn't have enough diagrams in there, I guess, but this is a WALT refresher. For task utilization, we keep track of n execution windows per task, and we derive a demand attribute. This demand attribute is, we impose a policy on it that's a tunable really, where you can say, look at the demand over the past 5 windows and take the average of that, or look at the most recent window, if that's higher, use that, and those kind of policies. One important thing to note about WALT is that the windows of observation are synchronized across CPUs, which means that you need an appropriate time source to do that. Scheduler guided frequency, which we do with WALT, we basically aggregate load from all tasks that ran in the most recently finished window, so it's just the one single previous window that we're looking at for scheduler guided frequency. And that's the statistic if you look in the code, and the code is available both in the Android commentary as well as EAS Dev. You can find the code there. That's the statistic that we use. So we do have separate load tracking statistics for CPU versus task. Although we track the windows using the same code, what ends up being sent to the governor versus what is used for task utilization is completely different and separate. So these are the reasons why we do that. We do account for wait time and task demand. We don't do that for CPU utilization. Again, that's a tunable, so if you want to play around with it, you can. We do believe that mobile workloads can benefit from the separation. That's one of the reasons. When you start a task, you can actually modify task demand without having to affect the frequency. So you can affect placement without affecting frequency. Like I said earlier, these are some of the statistics maintained by WALT for the CPU run queue. That's the aggregate statistic, the prev runnable sum and the cur runnable sum. The cur runnable sum is just the execution in the current window. So when you roll over, you store that in prev runnable sum, and then you start over. Same thing goes for per task windows. So this is basically a bit of history, how we actually got here. Big Little was, well, we started working on Big Little a few years ago, and Srivatsa and Steve Muckle here decided that it would be a good idea to implement our own scheduler, and Srivatsa also decided that it would be a good idea to do window-based load tracking. I would say that we don't actually have, or I don't remember if we have concrete data from those days as to why we made the decision, but it seems to have been proven even 3 years later, so I think it's a good one. We've presented some prototype results comparing EAS plus WALT versus EAS plus PELT at Linaro Connect SFO last year. And obviously, it's been integrated into the Android commentary this year. So we've been asked, obviously, by various folks why we think it's better, apart from the data itself, the actual theoretical background. One term that Vatsa came up with, which I think makes a lot of sense, is task reclassification. If a task has been, a light task for a long time and suddenly it starts exhibiting heavy demand, we believe that WALT is much faster at classifying it as a big task compared to PELT. We believe, when I say conservative approach in the second point, I'm talking about how PELT leaves the blocked utilization on the run queue and decays it slowly over time. We believe that whereas WALT actually removes the load and restores it for task demand when the task is back on the run queue, we believe that that is more appropriate for mobile use cases. The math is simpler, according to me at least. I don't know if anybody agrees with that, with WALT. You do have to think a lot about window rollover, and there is some complication there, but at least it's not a geometric series. You can add two numbers without thinking too much about it. So, like I said earlier, this presentation is really about integrating the WALT frequency metric, or the frequency statistic, with schedutil. I've noted down some important points about schedutil, most important being how it decides the next frequency. There was some discussion about that formula upstream when the patch was merged. So basically, it's using an 80% tipping point. So you take the, if your utilization is frequency invariant, the freak variable there is basically the max, CPU freak max frequency. So you multiply that by 1.25 and then multiply that by the utilization fraction. Schedutil also supports atomic context freak switching. I don't know if that's exactly the right way to do it, right way to term it. What I really mean to say is that you can actually change frequencies from the scheduler context if your hardware supports it without having to schedule a separate work queue or a separate context to do so. Schedutil frequency changes are triggered when the CFS fair utilization changes, i.e. when it is decayed or during migration if the utilization is removed. So what we've changed for WALT is basically we've tried to change nothing. We don't want to add anything fancy, no policies about what schedutil is doing. We just want to take the WALT utilization and provide it directly to schedutil for a fair comparison. So x86 does support atomic context frequency switching in hardware. So we did want to retain that capability. We didn't want WALT to make that not possible. WALT used frequency transition notifiers, and schedutil basically prevents atomic switching if you have, or fast switching, that's what they call it. They prevent fast switching if you have even a single transition notifier registered, so we removed that. I've also added another call site for invoking the frequency change, and that's when the WALT statistic changes. I found that just doing it on the PELT statistic, when the PELT utilization average changes, does not make sense for WALT. So this is a simple example that I've come up with. Again, I wish it was graphical, but bear with me. This is an x86 machine which has a minimum frequency of 1.6 gigahertz and a max of 3.4 with 200 megahertz steps. So since the frequency tracking is invariant, if you remember that formula, we use the 80% tipping point. So you basically take the max frequency, add 25% to that, and that's your basically your factor to which you multiply the utilization fraction. So if you execute for a full window at 1600 megahertz, WALT will classify that as a 46.9% task, and then the next frequency is simply 2 gigahertz by that equation, and that's how it proceeds. So within 1 to 3 windows, you can hit your Fmax in this particular test case. And I've used a 10 millisecond window here, so for this example, so basically that's 30 milliseconds. I mean, that's also assuming that your frequency changes are perfect and your windows line up perfectly with your load. So there could be some skew there, and you might have an extra window or two before you hit the Fmax mark. I've run through a lot of slides, so if there are any questions. Yeah, we added that for WALT, but I've tested with both with and without frequency invariance for WALT. So this is finally some graphical stuff so you don't fall asleep. This is basically a trace that's loaded in the Chrome browser. I've compared 2 window sizes, 5 milliseconds and 20 milliseconds, just to show how the ramp up and ramp down time changes. The first one is obviously PELT with the 32 millisecond half-life, which I have not changed. It would be interesting, I suppose, to compare to the 16 millisecond, or to try to change the PELT half-life and make a comparison. But this is what it is. So as you can see, there is some skew. It's not exactly 3 windows for when the window size is 20 milliseconds. There might be a little skew before you actually hit Fmax. Same goes for the 5 milliseconds. I don't know if anybody will actually use a 5 millisecond window. That's pretty aggressive. But if you, for some use case, if you wanted to meet on-demand performance, for example, I think it could make sense.
Vikram, do you want to clarify the point of the previous slide? That the ramp up is faster, is it slower, or how long?
Well, actually, if you look at it, so schedutil plus PELT and schedutil plus WALT with a 20 millisecond window, there is not that much of a difference, simply because of how schedutil does the ramping. But I guess the point of this slide is you can actually tune your ramp up time using the window size. Basically, it's very easy to use, tunable for your use case. I don't really know what the right window size is for x86 for server use cases. That's something that has to be investigated.
So is that when the basically utilization goes to 0, how does it move the ramp down?
Why is it a stepwise instead of going down all the way to zeros? For WALT, right? So it depends on the windows. So if the window is perfectly lined up, such that your previous window was max utilization and then one window later you had no utilization, it would immediately drop the frequency. But if your windows are not lined up perfectly, it can take some time. So it's just a matter of lining up the windows. So basically, if you look in the second one, right, schedutil plus WALT, 20 milliseconds, when the task stops executing, it might not be the end of the window exactly. It might be halfway through the window, for example.
And I guess for PELT, the problem there is that maybe the CPU goes idle, so we basically don't know.
Yes, so I have actually, so if you see those weird small lines there, that's actually my fake task trying to trigger a CFS RQ utilization change. But it does take longer always than WALT, yeah. In fact, that's one of the significant differences that we'll highlight later. So this is detailing some of the integration. Like I said earlier, we've removed the task utilization patch. The reason why we did this is to not only reduce the patch size, but to present something simple and something that upstream maintainers can just pick up and run if they really wanted to. We sent an email out to EAS dev, and I believe Dietmar just took out the patch, ran it on his x86 machine almost the same day, which is, I think, what we really want when we push this upstream. Like Steve Muckle said, the ARM targets are not very upstream ready for testing, so. So this is more of a demonstration how the code would look and how the stats accumulate. It's basically what is there on the Android commentary minus the task utilization and some refactoring to make it more upstream amenable. So that's what we do. We basically just take the prev runnable sum, that's the aggregated CPU utilization in the previous window. We directly pass that into schedutil without any policy or without any massaging or anything of that sort. So during migration, WALT has a need right now to take both the source and destination RQ lock, which is an expensive operation. We did try to reduce the amount of code that executes under the lock to make that more friendly, but obviously I think the consensus is that we need to not do that at all and just use a single lock and never basically take double RQ lock to migrate statistics, to migrate WALT statistics between source and destination run queues. So yeah, I'd like to thank the ARM guys and anybody else who's reviewed the patch on EAS dev. It's available for anybody else to review as well or test out. So the main points that we want to fix is the double locking. That's one suggestion that's off the top of my head. We also want to address the fact that not all architectures have synchronized clocks across CPUs. We're using K-time right now. We want to use get clock and get rid of that requirement as well. The third one should be easy enough to do. We need to integrate with the ARC freak invariance and ARC efficiency invariance APIs. We also have, so WALT is totally event-driven. We basically update statistics when the next task is selected and the previous task is taken off the run queue. And we have like event codes, and we want to get rid of those and just use the on RQ or the existing flags to do that. So 3 and 4 should be relatively easy to do. 2 is a bit more long-term, and 1 is an immediate requirement for upstream. Okay, so this is some data on x86. I'm personally very new, and I think a lot of people are new to x86 here. Honestly, this is just preliminary data. For power testing, I've used the RAPL counters. It's not actually measuring real power with hardware. This is just the on-chip counters. I've used the Phoronix test suite. I found it to be, some of the tests are kind of outdated. They've been updated like 2 years ago or a year ago. But overall, I believe it's like one of the best mass testing frameworks I've seen, simply because it's very reproducible, very easy to use. The dependencies are very easy to install. Of course, it's x86, so I guess they have that advantage. But yeah, I think the Phoronix test suite is something that we should probably try to imitate for ARM as well. I do believe they have some ARM devices in there right now that they're testing. But yeah, it needs to be much more large scale for ARM and upstream. So we integrated WALT on 4.7 RC6. I really need to update that. That's kind of old right now. The distribution that we use, the Linux distribution was Ubuntu 16.04. I just use that because that's what we use internally in Qualcomm as well. So coming back to frequency invariance, on x86 it's pretty strange for someone who's worked on ARM a lot. The hardware actually does a lot of work with respect to, even if you use the software governors, there's a lot of things going on in hardware. Even though CPU Freak has a separate policy, if you take an 8-core machine, CPU Freak has a separate policy for each CPU, and you can actually have a different vote. The actual frequency that each CPU runs is basically the aggregated max of all the active CPUs vote. So if you have 2 CPUs and one CPU is voted for 2 gigahertz and goes to sleep, the frequency is changed under software, in the sense that software doesn't know about it, to the other frequencies vote if it was lower. There's also something called turbo boost. So depending on the number of idle CPUs, you might actually overclock your CPU frequency, something that's something that's actually higher than what's listed in the scaling available frequencies. So if you have an x86 laptop right now and you cat your scaling available frequencies, you'll notice a very strange one at the top that's just 1 megahertz above the next closest one. So it's 3.4 gigahertz, and then it's 3.41 gigahertz for some reason. That 3.41 allows the enabling of this turbo boost mode, which can take your frequency up to something like 3.8 gigahertz as well. The only reason I figured this out is because I ran like a simple sysbench, and I found varying results depending on the number of idle cores. And then obviously the internet helped. So when we did frequency invariance on, with the WALT patch, I decided that we needed something more accurate, so we used the Intel performance monitoring counters. And those are pretty well supported, and there's a single instruction that you can use to read the cycle counter. The problem there is that, the one problem there is that you can't read, or at least I haven't been able to read a remote CPU's counter, so I have to make sure that each CPU tries to keep its counter updated as much as possible. That adds some overhead, which I can try to reduce, but I don't know if upstream even cares about this because it doesn't seem to affect test cases all that much. But I do believe that if you go into things like frame latencies or what's the exact word for it? Percentiles, yes. Then those kind of use cases should be affected by inaccurate load tracking. So these are some actual results from Phoronix. There's like a ton of tests, and I have results for all of those, but if I put them there, nobody would remember a single one. And I doubt you'll remember these as well, because the results are kind of the same for all these three combinations. I've tried different window sizes for WALT, just to see if it would make a difference, but these are pretty CPU-intensive use cases, except for probably FFM for the MP4 encoding. All of these show relatively the same performance with these governors and with WALT and PELT. So these are some of the graphics or gaming benchmarks which actually shows useful FPS information. We did see some power savings with WALT on the Open Arena one, not too much with Invariants, but still consistently lesser power. For Unique Engine Valley, which is a much more complicated 3D scene with a lot more objects, I guess, a lot more polygons or triangles, or how you want to put it. The power was almost exactly the same, and so was the FPS. For Tesseract, the second one, PELT frequency residency is considerably higher, and the power is considerably worse. So that's why you have this abnormally high FPS number. I haven't been able to figure out how to restrict these FPSs to VSync once I switch to the NVIDIA driver for my machine. When I use the open source, the upstream Nuvo driver for NVIDIA graphics cards, the FPS numbers dropped radically. I've just included the power numbers to basically show that it's just on demand keeping the frequency high. But I don't think those are relevant. So basically, the takeaway from this slide is the FPS numbers are also more or less the same between these three configurations. So this is some test cases that I came up with just to be able to measure power. What I do is just start a HTTP server on the local subnet, which hosts these videos. This is the Big Buck Bunny usual, pretty standard video. And then the machine that's running schedutil or any of these configurations loads up that video in a browser and plays about 2 minutes of video. So this is testing both the network stack power as well as the video decoding power. We see huge savings for 1080p with WALT. I have not been able to get something like frame latencies or percentiles or something like that. That'd be better statistic. But there were no frame drops, so I guess that's something. But ideally, to believe this data, I would also want to look at rendering latencies or something that's, that I can try to find on x86. When you switch to 4K videos, the power becomes pretty intense, and the differences between them, between the three configurations disappear. But yeah, if you watch a lot of YouTube, I suggest you switch to schedutil to save some power on your laptops. The other interesting note here is that Firefox seems to be way worse at power saving than Chrome. I have no idea why. But I think it's just, I don't know if it's using the same decoder as Chrome is using. So the takeaway from this slide is there is definitely potential for lower power for WALT, but we need more complete data to confirm this. I'm trying to also look for more interactive test cases on x86. There are a couple of browser-based benchmarks. There's in fact a Chrome rendering latency benchmark, but those do not give me consistent results, so I have not included them. But hopefully by the time LKML comes around, I can try to include something that concretely, without doubt, shows the difference.
I apologize if you covered this already. How is on-demand? What's the sampling window, like configuration for these on-demand and WALT options?
For WALT, the window size was 20 milliseconds. For on-demand, I honestly don't remember. It was just the stock thing that came with Ubuntu. So I can look that up and add that in. So I also did VLC video playback, similar to the test previously, but this just uses a local video file instead of streaming it over the network. There was not that much of a difference between PELT and WALT, but again, for 0 frame drops, schedutil saves way more power than on-demand. So yeah, if you watch a lot of video, you should switch to schedutil. The interesting thing here is that I haven't included the 2160 or the 4K video, because both schedutil plus PELT and schedutil plus WALT actually start dropping frames, which makes sense because on-demand just keeps the frequency high, and it has enough hysteresis to take care of this use case. But I think this is a pretty important use case because it highlights a real difference between schedutil and on-demand. And I'm trying to actually get, I've sent an email and I'm trying to get the Forensics guys to include something like this. So the conclusions, the main conclusion from the data itself is that we do believe that perf per power is likely better, but we need more data. The real advantage of WALT is really going to be the task tracking rather than frequency guidance. Like I said, this is just to make the patch set simple and have a working prototype that the upstream maintainers can actually run and see how the window stats are accumulated. We hope to post real data on a very pertinent ARM device, I would call it, pretty soon. And that should really clear any doubt about WALT versus PELT. The actual next steps for the patch itself, like I highlighted earlier, is to eliminate double locking, integrate the invariants APIs, and attempt unsynchronized. We want to do the double locking and the upstream invariants APIs before LPC for sure. We're trying hard to get to that point. For attempting unsynchronized window patches, I think that's, we won't delay our posting just because of that. So that's about it for me. It's a pretty short presentation, I guess. Any questions?
Did you get any data running the Hackbench or this kind of benchmark?
Yeah.
Because I mean, it should show or not overhead in adding this thing.
So I did not actually see a difference between when I ran perfbench and hackbench between the numbers, which is why I didn't really put them up here, because I wanted to show real world use cases. But I will try to put that up on when we post the patch, obviously.
Yeah, I mean, yeah, all the scheduler.
Right. Yeah, I think I ran the perf sched messaging thing, and there was really not much of a difference. One thing that we also want to do is actually instrument the WALT load tracking functions themselves, like the math in the WALT, and see how much of an overhead it is versus the PELT update load average, for example. So even if we don't see an end difference in the overhead or the real world use cases, we can at least try to establish if there is some overhead that we're adding that way.
This is perhaps slightly off topic, but you mentioned the fast switch, right, and how you guys did some modifications to WALT to make sure you didn't have a regression there. Is there any data out there on how big a difference that really makes, doing the transition from within the scheduler context versus spawning it out?
I have not seen data and I have not measured it personally. It was just from a theoretical point of view, we wanted to make sure our load tracking was accurate, but we do intend to measure that as well.
I was talking to one thing I kind of got to know today from Steve Muckle was that I think when they don't do fast switching, the thread that's running is a normal priority thread. So it could be superseded by any other higher priority thread or RT threads. So that's going to add a lot of latency depending on the condition. So maybe if you do make it a RT thread, it might not be a significant difference, but at least the way it is right now, I would believe it'll be, at least depending on the use case, it could be significant.
So yeah, I think given that I don't know if there's any ARM device out there that has fast switching, we really don't have data, but I think it should make a difference for mobile workloads, honestly.
Is there any data about the I/O related test or app launch?
Oh, do you say I/O testing?
Yes.
So I/O testing, at least from the Phoronix x86 benchmarks, I did not see a difference. But we'll probably post data on the ARM device soon, and then we should be able to see some differences there.
And you mentioned the wait time would not be count in the CPU time, but count in the task demand, right? So it includes the IOBC.
Is the
IOBC time.
I/O wait time?
Yes.
Yeah, we do have a tunable that allows you to include I/O wait time as well. They seem to have like some ARM devices listed, so I think they are trying at least. But honestly, if we could get like an ARM farm that all of us could just queue tests and run it and get results, that would be ideal. It'd be a great world to live in.
Do a bunch of 96 boards. That's all.
Yeah, but I think it's to everybody's advantage also. If everybody's really trying to converge upstream, then OEMs and vendors and my company, of course, should be really interested in this.
So your LKM posting,
Just wanted to broach the topic so that others in the room can also, because we kind of know this already, right? So you're building up to make a posting on LKML where between ARM, Linaro, and Google, all of us, we want to try and help, right? So you've mentioned next steps over here. Is your intention to close out all of those before you do your posting ahead of the LPC? Or?
So like I said, we want to close out the double locking thing,
Okay.
and we want to close out the invariance APIs.
Okay.
I think those should be pretty simple enough to do.
Right.
But the unsynchronized clock sources is something that we'll have to, I don't think we'll be able to get to it finish it before.
But that's
LPC.
okay, right? We can call that out as a to-do thing, right?
Yeah.
And in terms of the data, I think we've got substantial data now, right? Do we intend closing out with further analysis?
I do
before
want
your first
to,
posting? Or?
I mean, I do want to provide some real x86 data
Okay.
differences,
Right.
because like we discussed, right, real world use cases,
Yeah.
but something that you can actually run, and a maintainer himself can run, that would be ideal.
Okay.
But yeah, we do have sufficient data on for example.
Okay. And finally, for the benefit of others, the intent is that basically we're going to circle around what should be the text for the posting, right? In terms of, it's kind of a summary of your presentation, right? It's like, here's why WALT is better kind of thing, and here's some data to support that argument, right? Cool.
I would also say that, for example, the slides where you basically were saying that in like 3 windows you reach the max, so it's kind of mathematical property of the WALT compared to PELT. So something like this, like comparing mathematically WALT and PELT on a simple example would, I think, help.
Okay, that's a good suggestion. I'll take that.
So do you have any smartphone data showing that WALT is better, watt, energy per watt?
Yes, we do. The only thing is just how we release the data. We hope to do that pretty soon.
Because this is the Intel platform.
This is the Intel platform. The reason it's Intel is because the upstream maintainers are all working in Intel, so I want them to be able to actually make this relevant to them. But obviously our strong suite is the mobile workloads, ARM data, which we plan to release pretty soon.
Thank you. So why
Sorry,
for 4K, the watt loss is effectiveness is about the same as
I think the CPU usage is pretty intensive. Yeah, I think I don't know how much of the actual hardware is being used for the decoding, but as far as I can look at the frequency residencies and the busy time of the CPU, it's pretty intensive compared to the 1080p case.
How costly do you think the frequency invariance feature is to add? So I actually would find that useful as well,
Right.
For some of the stuff I'm working on. And yeah.
So right now, it actually reduces the absolute values of the benchmarks quite a bit, because I've done it, because I mean, it's a horrible implementation right now because I didn't care about absolute numbers. What I've done is whenever the RQ clock is updated, I've read this register, which is insane. So I think if we just keep it updated in the tick path and the NQ, DQ, and a few other places, I think the overhead should not be that much, and the accuracy should be good enough, is what I feel, but that needs to be evaluated.
Okay, and then as a follow-up to that, I'm just sort of morbidly curious, what kind of reaction are you expecting to all of this when it hits the list?
Yeah, we've just wanted to replace this thing that's been working for 4 years. So yeah, I think the reaction is going to be pretty explosive, maybe. But if we build up enough, if we have good enough theory and good enough data, and we don't do something that immediately pisses them off, then I think we should have something of a shot. I do believe that obviously the first question is why can't we make PELT better? And everyone is trying to, ARM and Linaro are trying to address that as well, I guess.
What's your best guess if you had to put a timeline on how long you think it'll take to get this, assuming you can get it in? How long do you think that battle will last?
Honestly, I don't have enough experience to answer that question, actually.
So you're probably going to say the same thing, but I'll say it anyways, right? So I don't think we should necessarily set our ambition at replacing PELT with WALT, frankly, right? So I think what we're really trying to do is start the conversation which results in PELT being improved for mobile. And I think you guys will agree that if that does happen, which in itself is also quite a lofty ambition,
Absolutely.
that'll be a happy outcome for all of us, right? Yeah.
Yeah, from a data point of view, we're going to be very ambitious. From a patch point of view, we're going to be very less ambitious.
Yeah, I mean, I agree. Somewhat similar. I was actually going to ask if you are going to position the RFC like we want to replace PELT, or we want this thing maybe to be alongside PELT. This kind of, I don't know if you.
So we have given that a bit of thought. Right now, we're not going to say either way explicitly. We're just going to say these are the mobile workloads, these are the data. We do believe there are shortcomings with PELT. WALT is an alternative that you might want to consider, and then we start the conversation. Like you said, it's obviously about just starting the conversation. I think that's most important. Yeah.
I think one other point. Vikram mentioned having good data and a decent amount of patch sets would be a good way to start moving the conversation, but I think equally critical part is maybe more ARM vendors can speak up and say, hey, this would help us out. We see the same issues too, instead of just being Qualcomm saying, hey, we see these issues. I think that'd be a really good point to try to move this ahead to.
So Thomas, perhaps you can help us with that. So perhaps you can, in a public forum, just say that, yes, our engineers will send a tested by for some of this stuff on LKML. You don't have to answer to that. I'm just winding you up. Right? But he's got a good point, right? I mean, like right now it's Qualcomm and Linaro and us. So on the other hand, if and by the way, there's a classic example of how one or two vendors providing tested buys on LKML helps, right? This is like last month when we had, which patch set did we get an act from Renesas and an act from somebody else, and that's it. Like in a couple of weeks, the patch was merged, right? So okay, that's another kind of patch, etc. But what I'm really saying is that if you get more support, just as Saravana was saying, it makes a big difference. Sorry, I used you as a cheap shot target, right? So.
Okay, I think we're done. Thank you for listening.